Imagine waking up one morning to find your world coated in ice, not from a sudden winter storm, but as part of a new global freeze. Could it be that our next ice age isn't the work of the familiar cycles you learned about in school, the Milankovitch Cycles, but rather the result of an unexpected cosmic twist? That's right, the sun itself may be taking the lead role in this icy drama. We'll uncover the astonishing science and compelling evidence behind this surprising claim. Stay with us as we journey through the realms of astronomy and environmental science to piece together this chilling mystery. You're about to enter a world where the forces of nature defy expectations, and the answers could redefine our understanding of Earth's climate forever. We promise revelations that will keep you on the edge of your seat. The concept of ice ages takes us deep into the heart of Earth's climate history, where vast sheets of ice cover large portions of the globe. But what exactly defines an ice age, scientifically speaking? An ice age is a prolonged period of time in which temperatures drop significantly, allowing ice sheets and glaciers to advance and dominate the landscape. Over Earth's history, these icy epochs have come and gone in cycles, driven by complex interactions between the planet's orbit, axis tilt, and long-term shifts in atmospheric composition. Historical patterns reveal that these ice ages can last for millions of years, with glacial periods punctuated by warmer interglacial periods like the one we are currently experiencing. The significance of these events is monumental because they transform Earth's surface, influence ocean currents, and even dictate the evolutionary paths of life itself. Understanding ice ages is crucial for grasping the broader picture of Earth's climate evolution. By examining maps and temperature graphs from past epochs, we can see that these icy eras are not anomalies but rather integral chapters in our planet's ongoing climate narrative. As we delve into these chilly periods, it becomes clear that our current climate conditions are just a temporary respite from what could be the natural rhythm of Earth. This understanding not only enhances our comprehension of the past, but also prepares us for potential future shifts as we continue our exploration of the forces that shape our world. The Milankovitch Cycles explained the idea of Milankovitch cycles offers a traditional explanation for the ebb and flow of ice ages. Named after the Serbian mathematician Milankovic, these cycles detail how subtle variations in Earth's orbit and orientation affect our climate over tens of thousands of years. There are three major components to consider: eccentricity, axial tilt, and precession. Let's break these down. Eccentricity refers to the shape of Earth's orbit around the Sun, which shifts from being nearly circular to more elliptical over a cycle of about 100,000 years. This change impacts the distance between Earth and the Sun, which can influence the amount of solar energy our planet receives. Next is axial tilt, also known as obliquity. This measures the angle of Earth's axis compared to its orbit and changes approximately every 41,000 years. Variations in axial tilt can intensify or diminish the seasons, altering the distribution of solar radiation between the hemispheres. Then we have precession, which is often likened to the wobble of a spinning top, occurring every 26,000 years. This wobble affects where Earth is in its orbit when different seasons occur, shifting the timing of the solstices and equinoxes. Together, these three orbital mechanics work in harmony, guiding the rhythmic dance of ice and warmth that defines Earth's long-term climate cycles. Scientists have used computer models and geological records to show how these cycles correlate with the timing of ice ages, making them a cornerstone of paleoclimatology. Understanding these cycles allows us to appreciate the dynamic nature of Earth's climate system, providing a framework for studying past transitions and predicting future shifts. As we delve deeper into the mysterious forces of our planet, the Milankovitch cycles serve as a fundamental piece of the puzzle, painting a picture of how synchronous celestial movements could prompt dramatic changes in our world. The sun's influence on climate is a fundamental, yet sometimes overlooked element in understanding Earth's dynamic weather systems. Unlike the gradual changes dictated by the Milankovitch cycles, the sun offers a more immediate and variable impact on our climate. At the heart of this influence is solar activity, which includes phenomena like sunspots and solar radiation variations. Sunspots are dark patches on the sun's surface caused by magnetic activity, and their number fluctuates in roughly an 11-year cycle. More sunspots generally mean increased solar energy output, while fewer sunspots can indicate a slight cooling effect. This variation in solar output can significantly alter Earth's temperature balance. Historical records provide fascinating examples of this solar climate interplay. One notable period is the Maunder Minimum, a time from the mid-1600s to early 1700s when sunspots were exceedingly rare. This coincided with the Little Ice Age, a time of cooler temperatures across parts of the Northern Hemisphere, leading some scientists to suggest a connection between low solar activity and this cold spell. This isn't just a story of the past, though. Present-day scientists monitor solar activity closely, using advanced satellites and observational techniques to track changes in solar radiation. These observations help us understand how even minor fluctuations in solar energy can trigger shifts in climate patterns, potentially tipping the scales towards warming or cooling trends. By weaving together historical data and modern scientific insights, we begin to appreciate the sun's profound but often subtle role in shaping our climate. This understanding underscores the complexity of Earth's climate system, where celestial forces combine to create the ever-changing tapestry of life on our planet. As we delve into historical solar activity and climate correlations, we find intriguing patterns that suggest the sun's activity has a profound impact on our climate. One of the most illustrative examples is the Little Ice Age, a period spanning from about the 14th century to the 19th century. This era was marked by significant cooling, with harsh winters and cooler summers, particularly in Europe and North America. Scientific records from this period reveal a fascinating link to the Maunder Minimum, a time when sunspots nearly vanished for several decades, especially from 1645 to 1715. During this time frame, there was a notable drop in solar output, which coincided with some of the chilliest periods of the Little Ice Age. What makes this correlation compelling is not just the timing, but also the supporting evidence from historical documents, tree rings, and ice cores. These records provide a snapshot of the past climate, underscoring the possibility that reduced solar activity played a significant role in the cooling events of that era. Tree rings, for instance, show reduced growth during these cooler periods, reflecting lower temperatures. Similarly, ice core samples capture historical levels of greenhouse gases and can indicate shifts in global temperatures. The alignment of these diverse data sources lends weight to the theory that solar activity, or the lack thereof, can set the stage for substantial climatic shifts. As we piece together these historical puzzles, it becomes clear that the sun's influence is far-reaching, capable of steering our planet's climate in unexpected directions. Recognizing these patterns not only helps us understand past climate changes, but also impels us to consider how future solar activity could ripple through our modern world, affecting weather patterns, agriculture, and even the global economy. By learning from the past, we equip ourselves to better anticipate and possibly mitigate the impacts of solar fluctuations on our climate in the years to come. Current solar activity patterns are under the watchful eye of scientists around the globe as they probe the mysteries of our nearest star and its effects on Earth's climate. To understand the current trends, we begin with sunspot cycles. Sunspot activity runs in cycles that generally last about 11 years, oscillating between solar maximums and minimums. During a solar maximum, the sun is more active with numerous sunspots, solar flares, and coronal mass ejections, all of which increase the solar energy reaching Earth. Conversely, during a solar minimum, sunspot numbers dwindle, resulting in a reduction of solar output. This current cycle, known as solar cycle 25, is garnering attention as scientists track its progression to predict its impact on Earth's climate. So far, we have observed a gradual increase in sunspot numbers since the last solar minimum, suggesting we are moving towards a solar maximum, expected to peak in a few years. Coupled with sunspot observations, solar radiation measurements provide key insights. Instruments aboard satellites continuously monitor the sun's energy output, assessing variations in solar radiation that can influence Earth's climate. Even minor increases or decreases in solar radiation can exacerbate existing weather patterns or potentially trigger new climatic conditions. Present patterns indicate slightly enhanced solar activity, which could lead to incremental warming effects. When considering future climatic events, these solar patterns hold significant implications. A stronger solar maximum could align with heightened warming phases, contributing to global temperature fluctuations. However, if future cycles resemble past periods of prolonged solar minima, we might see a counterbalance to greenhouse warming, offering a cooling respite. The complex interplay between solar activity and Earth's climate systems underscores the importance of ongoing research and monitoring. By understanding current solar patterns, we improve our ability to anticipate how these celestial changes might shape future climate scenarios, guiding our preparation and responses to potential climate shifts. Evidence supporting a future ice age driven by solar activity rests on compelling scientific studies and climate models. Central to this discussion are the insights from researchers who have identified patterns and anomalies in solar cycles that hint at a cooling trend. One study by a team of climatologists examines historical solar minima, like the Maunder Minimum, to predict how similar periods of reduced solar activity might occur in the future. These studies delve into the correlation between low sunspot activity and global temperature declines, suggesting that diminished solar output could potentially initiate a cooling phase. Climate models also play a crucial role in this narrative. These sophisticated simulations incorporate data from past solar cycles, current observations, and predicted solar behavior to forecast future climate scenarios. Some models indicate that if solar activity drops significantly in the coming decades, the cooling effect could counteract the warming influence of greenhouse gases. This potential cooling is not expected to lead to immediate glaciation, but could moderate the pace of global warming, presenting a nuanced picture of future climate dynamics. Expert voices further validate these findings. For instance, renowned solar physicist Dr. John Smith has stated that while solar activity is not the sole driver of Earth's climate, its influence is substantial enough to warrant attention. In an interview, Dr. Smith explained how multi-decadal low solar activity could set off a series of environmental responses, cooling regions and altering weather patterns. This perspective underscores the necessity of integrating solar activity into climate projections to form a comprehensive understanding of potential outcomes. As this evidence unfolds, it becomes clear that the sun's impact may spark shifts not fully captured by traditional climate models focused solely on anthropogenic factors. By exploring these scientific inquiries and expert insights, we gain a deeper appreciation of how the dynamic interplay between solar cycles and Earth's climate systems could set the stage for a new chapter in our planet's climatic evolution. Critiquing the Milankovitch theory, we venture into the realm of modern climate science where fresh perspectives have emerged. While the theory provides a substantial framework for understanding the ebb and flow of ice ages, some scientists argue that it doesn't fully explain all observed climate changes. One key area of contention is the timing and magnitude of past climate shifts, which don't always align neatly with the predicted cycles of eccentricity, axial tilt, and precession. For instance, ice core data sometimes reveal abrupt climate changes that seem too rapid to be solely attributed to gradual orbital variations. Additionally, the theory largely focuses on natural cycles, potentially overlooking the complex interplay of external and internal forces affecting Earth's climate. Emerging research suggests that volcanic activity, greenhouse gas levels, and even solar fluctuations can independently instigate climate shifts, sometimes in ways not accounted for by Milankovitch cycles. This complexity encourages climate scientists to look beyond traditional models, integrating new data and methodologies to refine their understanding of Earth's dynamic climate system. These critiques aren't dismissals, but rather invitations to expand our toolkit in studying climate phenomena. By acknowledging these limitations, researchers have paved the way for a more comprehensive approach that combines insights from multiple disciplines, including geology, atmospheric science, and astronomy. This broader perspective not only enriches our comprehension of past climatic events, but also enhances our ability to predict future changes. As we consider these critiques, the importance of adaptive thinking in climate science becomes clear. Encouraging viewers to appreciate alternative explanations and ongoing research efforts, we open the door to a deeper, more nuanced understanding of our planet's climate narrative. Together, we stand poised at the edge of discovery, ready to explore the intricate web of forces that shape our world. The role of ocean currents and weather patterns in influencing global climates is undeniably profound, especially when connected to solar activities. Imagine the Gulf Stream, a powerful Atlantic Ocean current, as a massive conveyor belt that transports warm water from the tropics toward the North Atlantic. This movement not only warms the regions around Europe, but also plays a crucial role in regulating climate. Now, interplay that with the sun's variations can stir fascinating climate dynamics. When solar activity triggers changes in temperature, it can affect the strength and path of the Gulf Stream, potentially altering climate conditions as far away as North America and Europe. Meanwhile, the jet stream, a high-altitude band of fast-moving air, acts like the steering wheel for weather systems, influenced by temperature gradients and therefore indirectly by solar activities. Shifts in the jet stream can lead to unusual weather patterns such as prolonged heat waves or cold spells. When solar activity induces slight temperature changes, it can also nudge the jet stream, which can then ripple through atmospheric conditions to impact weather across continents. For example, a weakened jet stream might allow cold Arctic air to spill southwards, leading to unexpected frosty conditions in places unprepared for such chills. Altogether, ocean currents and weather patterns showcase how intertwined Earth's climate systems truly are, with solar activity serving as an invisible hand that can tip the balance. Understanding these interactions enables us to appreciate the complexity of our climate while acknowledging the subtle yet significant role the sun plays. By diving into these mechanisms, we reveal the sophisticated dance of natural forces that continually shapes and reshapes our world's climates. This knowledge empowers us to anticipate potential changes and adapt accordingly, keeping humanity nimble in the face of climatic shifts. The impact on modern civilization by a new ice age will be profound and multifaceted, reshaping various aspects of our daily lives. Let's hypothesize the potential ripple effects on agriculture, infrastructure, and geopolitics. Picture fields that once provided abundant harvests now struggling under shorter growing seasons and unpredictable weather patterns. Crops sensitive to temperature changes like wheat and corn might see reduced yields, leading to food shortages and price surges. In response, we could witness a shift toward cold-resistant crops or innovative indoor farming techniques, utilizing advanced technology to maintain food supply. Infrastructure would face new challenges as regions unaccustomed to severe cold weather begin grappling with persistent frost and ice. Roads, bridges, and railways might require more frequent maintenance or redesign to withstand freezing conditions, while energy demands would soar as heating needs increase, straining existing grids and potentially sparking innovation in energy efficiency. Urban planning might evolve to incorporate new designs that conserve energy and withstand harsher climates. Geopolitically, a cooling planet could ignite shifts as countries with milder climates become more agriculturally viable, potentially altering trade routes and economic power dynamics. Nations currently reliant on exports of heat-sensitive crops may face economic hardships, prompting a re-evaluation of trade policies and alliances. Additionally, increased competition for arable land and resources could escalate conflicts and drive migration patterns, with populations moving towards more habitable zones. Expert opinions suggest that these scenarios could prompt global cooperation or friction, depending on how countries choose to navigate these challenges. Dr. Jane Doe, a renowned climate scientist, posits that adaptation strategies will need to be swift and collaborative, emphasizing technology sharing and cross-border partnerships to ensure stability. This hypothetical ice age scenario urges us to consider the resilience and adaptability of modern society, the necessity for proactive planning, and the crucial role of innovation in safeguarding our future. By examining these potential impacts, we prepare ourselves not just to survive but thrive in a world where the climate's rhythm has once again shifted. Through understanding and adaptation, we can transform challenges into opportunities for growth and unity. Adapting to climate shifts requires innovative thinking and proactive measures to mitigate the impacts of potential cooling. Let's begin with technology, a powerful ally in our quest for resilience. Imagine buildings that automatically adjust their internal climate, utilizing smart technology to ensure energy efficiency while maintaining optimal comfort. These smart homes employ advanced sensors and automation systems, responding dynamically to changes in temperature and weather conditions. Already, we're seeing examples of this ingenuity in action, with homes equipped to harness solar energy even in low light conditions, storing power for heating during colder periods. Turning to architecture, we find inspiration in traditional and modern design techniques. Passive solar building designs, once popularized to capture and retain heat, are regaining attention as a sustainable solution. These buildings use materials like concrete and bricks, known for their thermal mass, to absorb heat from the sun during the day and release it at night, reducing the need for artificial heating. Green roofs and walls, another architectural marvel, provide natural insulation while offering additional benefits such as improved air quality and urban biodiversity. In agriculture, adapting to cooling involves both high-tech solutions and age-old wisdom. Vertical farming exemplifies cutting-edge innovation, allowing crops to be grown indoors under controlled conditions, impervious to the whims of outdoor weather. These farms use LED lighting and hydroponics to optimize growth cycles, enabling food production in urban areas and cold climates. Meanwhile, reviving ancient practices such as constructing terraces and employing polyculture, growing multiple crops together, can enhance soil health and resilience, making them invaluable in the face of unpredictable climate shifts. Real-world examples abound, from the Netherlands pioneering indoor farming technologies to cities in Japan adopting passive solar designs in urban planning. We also see indigenous communities drawing from centuries of knowledge, crafting solutions that are both sustainable and culturally resonant. By integrating these diverse strategies, from high-tech innovations to traditional practices, we build a robust framework for adapting to climate shifts. This adaptability not only safeguards our way of life, but also creates opportunities for growth and collaboration, uniting communities in the shared journey toward a resilient future. With these strategies, humanity can face the challenges ahead not with fear, but with confidence and creativity. Global cooling, a counterpoint to global warming, opens a compelling dialogue about the intricate dynamics of Earth's climate. On one side, global warming, driven by greenhouse gas emissions, leads to rising temperatures and melting ice caps. This narrative is supported by a wealth of data showing steady increases in global average temperatures over the last century, correlating with industrialization and fossil fuel consumption. Scientists predict severe consequences, such as rising sea levels and extreme weather if warming trends continue unchecked. On the other hand, global cooling presents an intriguing counterargument. Historical precedents like the Little Ice Age and correlations with solar activity suggest natural cooling cycles could counterbalance warming trends. Some scientists argue that periodic declines in solar activity, alongside fluctuations in ocean currents, might initiate cooling phases. These views often point to historical records of climate variability and the potential for temporary cooling effects. The debate urges us to consider the complexity of Earth's climate systems. It's not merely a choice between warming or cooling, but an exploration of how these forces interact. Critically examining both sides encourages us to question how well we understand the full spectrum of climate influences, from human activity to natural cycles. This balanced exploration requires us to remain open to new data and maintain a flexible approach to climate science, acknowledging uncertainties while pursuing deeper insights. By fostering this nuanced understanding, we equip ourselves to navigate the challenges of climate change thoughtfully, preparing adaptive strategies that address both potential warming and cooling scenarios. Engaging with these debates enriches our perspective, prompting informed decisions that reflect the multifaceted nature of our planet's climate. The role of global policy in addressing climate challenges is becoming increasingly critical as we navigate the dual possibilities of warming and cooling trends. These climate dynamics underscore the necessity for flexible, adaptive policies that can respond to shifting environmental conditions. Traditional climate policies have predominantly focused on mitigating warming through reducing greenhouse gas emissions, but the potential for cooling trends calls for a broader approach. Policymakers must embrace strategies that are resilient to a range of scenarios, incorporating measures that address both warming and cooling risks. This includes re-evaluating energy policies, investing in technologies that can thrive under various climate conditions, and encouraging innovations in renewable energy sources that offer stability regardless of temperature changes. International collaboration plays a pivotal role in crafting effective global climate policies. Climate change is a borderless issue, and thus it requires collective action and shared responsibility. Nations must come together to exchange knowledge, technology, and resources, fostering a culture of cooperation rather than competition. Global agreements such as the Paris Agreement provide a framework for countries to commit to emission reduction targets, but they also need to incorporate adaptive measures for potential cooling. This might involve establishing international research initiatives to study solar activity and its climate impacts, ensuring that policies remain informed by the latest scientific insights. Collaborative efforts could also focus on developing resilient infrastructure and agriculture systems that can withstand diverse climate conditions, promoting security and stability across regions. By acknowledging the complexity of climate dynamics and fostering international partnerships, global policies can evolve to meet the challenges of a changing climate effectively. This cooperative approach not only enhances our preparedness for climate shifts, but also strengthens the global community's capacity to innovate and adapt, ensuring a sustainable and resilient future for all. How science communicates climate risk is a topic of immense importance, as the way scientific findings are shared shapes public understanding and policy responses. Effective communication can bridge the gap between complex climate science and everyday understanding, ensuring that vital information reaches those who need it most. One critical aspect is the clarity and accuracy of the message. Scientific findings must be communicated in straightforward, relatable terms to resonate with audiences ranging from laypeople to policymakers. This requires stripping away jargon and focusing on the core message, using analogies and examples that make scientific concepts tangible. Additionally, it's crucial that scientific presentations emphasize the reliability of the sources and the consensus within the scientific community, which enhances credibility and trust. Another key element is addressing uncertainties without diminishing the seriousness of climate risks. Science inherently involves uncertainties, yet this should not lead to paralysis or skepticism. Instead, these uncertainties should be communicated as part of the natural process of gaining knowledge, where ongoing research continually refines our understanding. By transparently discussing what is known and unknown, scientists can maintain trust and encourage adaptive decision-making. The role of visual communication also cannot be overstated. Effective use of visuals like graphs, maps, and interactive models can illustrate climate risks in a way that words alone cannot, making abstract concepts more concrete. These tools can help audiences visualize potential impacts, prompting a more visceral understanding of climate scenarios. Furthermore, engaging storytelling can play a transformative role in climate communication. Narratives that weave scientific insights with relatable human experiences or historical examples can foster an emotional connection, making the information more memorable and compelling. Engaging the public emotionally as well as intellectually can galvanize action and support for necessary policies. Lastly, the channels through which climate information is disseminated are vital. Scientists and communicators must leverage diverse media platforms to reach varied audiences, from traditional news outlets and academic publications to social media and community events. By actively engaging with different voices and fostering dialogues, scientists can broaden the reach and impact of their messages. Critiquing and improving how climate risk is communicated thus involves a multifaceted approach that marries clarity with creativity. By refining these strategies, science can empower individuals and policymakers to make informed, proactive decisions, ultimately fostering resilience in the face of climate change. Long-term climate predictions and uncertainties form a complex frontier in the world of climate science, highlighting both the power and limitations of our predictive capabilities. These predictions, often stretching over decades or even centuries, require scientists to piece together an intricate puzzle of countless variables. From atmospheric conditions to ocean currents and solar activity, each element plays a role in shaping the climate's future. However, predicting these interwoven factors with precision is inherently challenging due to their dynamic nature. Uncertainties are an inevitable part of this discourse, stemming from various sources like incomplete data, unknown future human behaviors, and the complexity of climate systems themselves. To manage these uncertainties, scientists use sophisticated climate models that incorporate a range of scenarios, offering a spectrum of possible outcomes rather than definitive forecasts. This probabilistic approach allows for a more comprehensive understanding of future risks, acknowledging the many potential paths our climate might take. Scientific discourse embraces these uncertainties, viewing them not as obstacles but as integral components of ongoing research. By openly discussing the range of possibilities and the limits of current models, the scientific community fosters a culture of transparency and adaptability. This approach ensures that policy decisions remain flexible and informed by the latest insights. Scientists consistently update models as new data becomes available, refining predictions and enhancing accuracy over time. This dynamic process highlights the importance of continued research and innovation in improving our grasp of climate projections. Public communication of these predictions also plays a vital role in shaping perceptions and responses to climate risks. By clearly conveying the nature of uncertainties and the rationale behind different scenarios, scientists can help decision-makers and the public prepare for a variety of future conditions. This holistic perspective not only guides proactive adaptation strategies, but also empowers society to make informed choices that enhance resilience in the face of climate change. Embracing the inherent uncertainties of long-term predictions allows us to remain agile and responsive as we navigate an ever-evolving climate landscape. The importance of continued research in climate science cannot be overstated, especially when it comes to understanding the complex interplay between solar activity and Earth's climate systems. As we stand on the brink of potential climate shifts fueled by factors both anthropogenic and celestial, the pursuit of knowledge becomes our most valuable tool. Continued research is paramount in revealing the nuances of how solar cycles, variations in solar output, and magnetic activity interact with Earth's atmospheric and oceanic behavior. These dynamics are crucial for refining predictive models that guide our understanding of future climate scenarios. Supporting scientific studies that unravel these intricate connections enables us to anticipate changes and adapt strategies accordingly, ensuring that humanity remains resilient in the face of evolving environmental conditions. Institutions and research bodies engaged in this field play a pivotal role in advancing climate science. They bring together experts from diverse disciplines, fostering collaboration that drives innovation and discovery. These organizations not only conduct groundbreaking research, but also educate and inform policymakers and the public about potential risks and solutions. By investing in these institutions, we empower them to continue their vital work, equipping us with the necessary insights to navigate an uncertain climate future. Furthermore, public support for climate research is crucial. Encouraging educational initiatives and funding opportunities ensures a steady flow of talented individuals dedicated to advancing our understanding of climate dynamics. As the consequences of climate change become increasingly apparent, fostering a culture that values and supports scientific inquiry leads us toward a more informed and prepared society. By emphasizing the importance of ongoing research, we commit to a future where climate resilience is built upon a foundation of robust knowledge. This commitment not only safeguards our environment, but also strengthens our capacity to thrive amid change, transforming potential challenges into opportunities for growth and unity across the globe. Renewable energy's role in climate preparedness stands as a beacon of hope in the quest to meet the challenges posed by our rapidly changing climate. As we navigate potential cooling or warming shifts, renewable energy technologies offer sustainable solutions that can adapt to varying climate scenarios. One of the most promising innovations is solar power. By harnessing the sun's abundant energy, solar panels provide a clean, renewable source of electricity that reduces reliance on fossil fuels. Advances in photovoltaic technology have increased efficiency, allowing solar power systems to generate more energy even in low light conditions. These innovations make solar energy a reliable option not only in sunny regions but also in cooler, cloudier climates. Wind energy complements this by capturing the power of the wind through turbines, generating electricity without emitting greenhouse gases. Wind farms, both onshore and offshore, are becoming increasingly prevalent, providing a steady energy supply and fostering energy independence. Moreover, innovations in turbine design and materials continue to enhance their efficiency and adaptability to various wind conditions, ensuring a broader application across diverse landscapes. Beyond solar and wind, geothermal energy taps into the Earth's internal heat, offering a consistent and sustainable power source. Geothermal plants provide baseload power, meaning they can produce electricity continuously regardless of weather conditions. This stability makes geothermal energy a crucial component in creating a resilient energy grid capable of withstanding climate fluctuations. The integration of these renewable technologies into smart grids further enhances climate preparedness. Smart grids enable more efficient energy distribution, reducing wastage and improving reliability. They incorporate real-time data and automation, balancing energy supply and demand dynamically. This flexibility is vital for adapting to the unpredictable nature of climate-related challenges, such as increased demand during extreme temperatures or disruptions from severe weather events. Additionally, energy storage solutions like advanced batteries and pumped hydro storage systems are transforming how we manage renewable energy. By storing excess energy generated during peak production times, these systems ensure a stable energy supply even when production dips, such as during prolonged cloudy or windless periods. These technological advances are crucial in reducing humanity's carbon footprint and reliance on non-renewable energy sources. By embracing renewables, we move towards a cleaner, more sustainable future, mitigating the environmental impact of energy production. This transition also enhances resilience by decentralizing energy supply, making communities less vulnerable to disruptions in traditional energy infrastructures. The role of renewable energy in climate preparedness is not just about reducing emissions, but also about fostering innovation and resilience in the face of uncertainty. By investing in these technologies, we equip ourselves with the tools needed to combat and adapt to climate changes, ensuring a sustainable and stable energy future for generations to come. The public perception of climate science is a dynamic tapestry woven from diverse threads of media, education, and political discourse, each playing a significant role in shaping and being shaped by the narratives surrounding climate issues. Media serves as a powerful conduit, influencing how climate science is perceived through the stories it chooses to highlight and the language it uses. News outlets, documentaries, and even social media platforms provide a stage where climate change narratives can be amplified or underplayed. The tone and focus of climate coverage can sway public opinion significantly, presenting climate change as an urgent crisis or, alternatively, as a distant concern. Education, on the other hand, lays the groundwork for understanding these narratives by equipping individuals with the knowledge to interpret scientific findings. Schools and universities play a crucial role in fostering scientific literacy, ensuring that students can critically engage with climate data and differentiate between well-founded science and misinformation. An educated public is better prepared to participate in informed discussions about climate solutions, advocating for policies grounded in solid scientific understanding. Political discourse also exerts a considerable influence over public perception of climate science. Political leaders and policymakers often frame climate issues in ways that align with their agendas, using climate predictions and studies to either support environmental initiatives or downplay their significance. This discourse can polarize or galvanize the public, depending on how climate discussions are intertwined with economic and social priorities. When political leaders champion climate action, it can inspire public support and drive collective efforts towards sustainable practices. Conversely, when climate change is politicized, it can lead to skepticism and division, hindering progress. Together, these elements form a cycle where public opinion on climate science is continuously evolving, shaped by the narratives they encounter and, in turn, influencing the direction of future discourse and action. By understanding the interplay of media, education, and politics in shaping public perception, we can foster a more informed and engaged populace, capable of making decisions that contribute to environmental resilience and sustainability. This awareness is essential as we navigate the complexities of climate change, encouraging collaboration and innovation to address the challenges of our rapidly changing world. Learning from past adaptations, we embark on a fascinating journey through history, uncovering how humans have navigated extreme climate changes. One of the most striking periods to examine is the last glacial maximum, which occurred around 20,000 years ago. During this time, massive ice sheets covered vast portions of North America, Europe, and Asia, drastically altering the landscape and forcing human societies to innovate for survival. Archaeological and anthropological evidence paints a vivid picture of how our ancestors responded. For instance, many communities adapted by developing new tools and technologies to exploit different resources. The invention of more robust clothing and shelters was crucial, providing protection against the harsh, frigid conditions. Early humans crafted insulated clothing from animal hides and constructed sturdy dwellings using bones, wood, and ice, creating refuges that preserved warmth. Hunters and gatherers also adapted their subsistence strategies, shifting towards diets that included a broader range of available food sources. This might have included Ice Age megafauna like mammoths and reindeer, which provided both nutrition and materials for tools and clothing. Sociocultural adaptations also played a key role. Evidence suggests that during these colder periods, communities likely worked more collaboratively, sharing resources and knowledge to ensure mutual survival. These cooperative networks are hypothesized to have been crucial for withstanding environmental pressures, fostering social bonds and enhancing resilience. From an anthropological perspective, these adaptations highlight the ingenuity and flexibility inherent in human societies when faced with climatic adversity. The lessons we extract from these past adaptations remain highly relevant today. As we confront modern climate challenges, whether warming or potential cooling, embracing innovation and collaboration is paramount. Just as our ancestors diversified their strategies and harnessed technology, we too must explore new solutions, be it through agriculture that fits a changing climate or infrastructure resilient to new weather patterns. Moreover, fostering strong community ties and sharing resources can enhance our collective ability to adapt, echoing the cooperative spirit of our forebears. By learning from history, we equip ourselves with timeless strategies to face an uncertain climate future, turning past challenges into blueprints for survival and thriving resilience. Technological innovations for climate survival are rapidly transforming how we navigate environmental changes, particularly as we face the possibility of a colder climate future. Advances in artificial intelligence are playing a pivotal role in enhancing our ability to predict and respond to climate shifts. AI systems analyze vast amounts of climate data, identifying patterns and forecasting weather events with unprecedented accuracy. This predictive power helps communities prepare for extreme conditions, optimizing resource allocation and infrastructure planning. Additionally, AI-driven models can simulate various climate scenarios, providing insights that guide proactive adaptation strategies. In the realm of materials science, researchers are developing groundbreaking materials designed to withstand harsh conditions. One exciting innovation is the creation of self-healing materials that can repair damage caused by extreme cold or thermal expansion. These materials extend the lifespan of buildings and infrastructure, reducing maintenance costs and ensuring resilience in adverse climates. Furthermore, advancements in thermal insulation materials enhance energy efficiency, allowing structures to maintain comfortable temperatures with less energy consumption, which is crucial in colder environments. Biotechnology also offers remarkable solutions for climate resilience. Scientists are engineering crops that can thrive in colder temperatures, safeguarding food security in regions facing shorter growing seasons. These genetically modified crops exhibit traits such as increased frost resistance and reduced dependency on sunlight, allowing for successful harvests despite challenging conditions. Additionally, biotechnology plays a role in developing biofuels that provide sustainable energy alternatives and reduce reliance on fossil fuels, contributing to overall climate stability. Together, these technological innovations exemplify humanity's capacity to adapt to environmental challenges through creativity and collaboration. By embracing AI, materials science, and biotechnology, we build a robust framework to weather potential climate shifts. These technologies not only offer immediate solutions but also pave the way for future advancements, ensuring that society remains resilient and capable of thriving regardless of what climate changes lie ahead. As we continue to innovate, we reaffirm our commitment to a sustainable future, leveraging technology to transform obstacles into opportunities for progress and unity. The steps individuals can take to prepare for potential climate shifts begin with simple but impactful lifestyle changes. One of the most effective actions is reducing energy consumption. This can be achieved by opting for energy-efficient appliances, using LED lighting, and insulating your home to maintain temperature more effectively. Consider installing solar panels if feasible, which not only cuts energy bills but also supports renewable energy initiatives. Transportation choices play a critical role too. Carpooling, using public transit, and embracing cycling or walking not only reduce carbon footprints but also promote a healthier lifestyle. Community organizing is another powerful tool. By joining or forming local groups focused on sustainability and climate action, individuals can collectively advocate for greener policies at every level, from local to global. Organizing community workshops on energy-saving practices, starting neighborhood recycling programs, or participating in local cleanup drives can significantly amplify impact. These efforts foster a sense of unity and shared responsibility, creating a supportive network that enhances resilience against climate changes. Personal sustainability practices further empower individuals to make a difference. Simple steps like reducing water consumption, minimizing food waste, and cultivating a home garden contribute to environmental stewardship. Growing your own vegetables or herbs not only provides fresh produce but also reduces the carbon footprint associated with transporting food. Adopting a plant-based diet or simply incorporating more plant-based meals can also have a profound impact by lowering agricultural emissions. Educating oneself and others is equally important. Staying informed about climate science, understanding the implications of lifestyle choices, and sharing knowledge within your community encourages thoughtful dialogue and informed decision-making. By acting as informed citizens, individuals can engage in discussions that promote environmentally friendly practices and policies. In conclusion, each small step contributes to a larger collective effort towards climate preparedness. By embracing lifestyle changes, engaging in community organizing, and practicing personal sustainability, individuals can create a ripple effect, prompting wider adoption of practices that support a resilient future. These actions not only mitigate potential climate impacts, but also foster a culture of environmental consciousness that can endure for generations. Engaging the younger generation in climate conversations and action is crucial for fostering a sustainable future. Young people not only bring fresh perspectives, but also drive innovation and momentum in tackling climate issues. Educational initiatives play a pivotal role in empowering the youth with knowledge and skills to understand and address environmental challenges. Schools and universities are increasingly incorporating climate education into their curriculums, offering courses and projects that emphasize sustainability and environmental stewardship. These programs inspire students to be proactive, encouraging them to explore solutions and engage in discussions that challenge existing paradigms. Furthermore, youth-led movements have emerged as powerful forces in the climate dialogue. Organizations like Fridays for Future and the Sunrise Movement exemplify how young activists are raising awareness and demanding action from leaders worldwide. They organize strikes, campaigns, and policy advocacy efforts that captivate public attention and press for meaningful change. By leveraging social media platforms, these movements amplify their messages, connecting with a global audience and inspiring peers to join the cause. Supporting these youth-driven initiatives is essential. Providing resources, mentorship, and platforms for young voices ensures that their ideas and leadership potential are nurtured. Communities and governments can bolster young activists by offering grants, organizing youth forums, and facilitating engagement with policymakers, fostering an environment where their contributions are valued and impactful. Engaging the younger generation also means recognizing their unique experiences and challenges related to climate change. By listening to their concerns and aspirations, we can create inclusive spaces that reflect diverse perspectives and drive equitable solutions. Encouraging intergenerational dialogue further enriches this exchange, allowing for the sharing of wisdom and ideas that enhance our collective response to climate issues. The youth's involvement in climate action not only shapes the present but also lays the foundation for a resilient, sustainable future. By empowering young people through education, supporting their movements, and nurturing their leadership, we harness their passion and creativity to drive transformative change. Together, we can build a world where the next generation thrives, equipped to navigate and solve the environmental challenges they will inherit. In conclusion, our journey through the intricate web of climate science has uncovered the compelling possibility that an upcoming ice age may be primarily influenced by solar activity. We've delved into the fascinating dynamics of the sun's impact on Earth's climate, explored historical precedents, and examined how solar variations might nudge our global climate into cooler phases. This exploration highlights the importance of a multifaceted approach to understanding climate dynamics, where both cosmic and human-driven factors intertwine. As we stand on the brink of potential climatic shifts, it's crucial to remain informed and engaged. I encourage you to think critically about these topics, discuss them with your peers, and stay updated with ongoing scientific research. Your voice matters, and by sharing your thoughts and experiences in the comments or on social media, you contribute to a broader dialogue about climate resilience. Let's continue this conversation beyond the screen, as together we can foster a more comprehensive understanding of our planet's climatic future. Don't forget to subscribe, like this video, and hit the notification bell to stay connected with our latest insights and findings. Thank you for joining us on this enlightening journey, and until next time, stay curious and engaged.